Hey guys, today we'll talk about mass energy equivalence, which is epic. You are made out of matter, and matter is a form of energy that is incredibly dense. You have so much energy contained within your atoms. It's insane. It's very hard to unlock for other purposes, possible. Most easily to unlock it all with things like antimatter. But because when antimatter combines with matter, they both annihilate and turn to gamma rays and stuff, releasing insane amounts of energy. Anyway, why don't we start with this formula? Super famous, E equals mc squared. The energy contained in matter is equal to its rest mass, or just due to the matter, is equal to its rest mass. It's mass that you would measure if you're at rest relative to it. Or at the center of momentum of the thing relative to it, if it's composed of a bunch of particles, which things usually are. All right, so energy is equal to the rest mass times the speed of light squared. Now, the speed of light squared is an insanely huge number. Mass is measured in kilograms, C is measured in meters per second, and E is measured in joules. So a kilogram of mass is equal to 3 times 10 to the 8 squared, which is 9 times 10 to the 16 joules. So if you could convert a kilogram of mass, you would have, purely to energy, you would be able to get 9 times 10 to the 16 joules out of that, which is insane. That's like enough to shift a planet. That is enough to extinguish all life on Earth if unleashed all at once. Like, it is a stupid amount of energy, and it's like contained in your shoe, like that much mass. It's ridiculous. Anyway, the universe is amazing. That's all I gotta say about that. Actually, no, it's not. The full formula for Einstein is the energy squared is equal to the momentum squared of an object times c squared plus the rest mass, or invariant mass, the mass when measured at the center of momentum, squared times the speed of light to the 4th power. This guy is pretty interesting because it implies things with energy have momentum, like light and other massless particles. So if you don't have this term, you can just square root both sides. So if you ignore this guy, take the square root of both sides, you end up with this. So if you have a massless particle like light, its momentum is equal to its energy divided by the speed of light. If you've ever heard of a concept called a solar sail, they may be the first thing we use to explore other planets, because what they do is they've got a shiny coating. You can make them out of aluminum foil pretty much, though sapphire coated ones I think are the go-to. If you have that in space, as light from the sun hits it and reflects back, that is a change in momentum. It's a very small change in momentum, but if you got enough light, it exerts a constant pushing force. And so there's this whole idea that you could send a probe to another planet by making an insanely powerful laser with great cohesion so it doesn't spread, and just like blasting the solar sail. And since you don't need to keep the source of energy on the craft itself, you could have like 1 million nuclear power plants powering the laser and just push it like crazy. Yeah, and so that's one of our ideas of getting to other galaxies. So insane amounts of energy contained in every matter everywhere, very hard to unlock. By the way, nuclear power plants work by like fission. You've got big nucleuses changing to smaller nucleuses, but plus a couple of free neutrons. But if you were to weigh the atom before and weigh the products after, there is a difference of about between 1 in 100 and 1 in 1,000. And that is enough to make nuclear weapons, nuclear power plants, like releases insane amounts of energy, and you're just using like 1,000th of the mass contained in the substance. And it's like the most powerful stuff we use here on Earth. By the way, if you're wondering why we don't use antimatter all the time, it's insanely hard to make and store. Insanely. The point where a few atoms is very difficult, though getting a little better. And last thing I want to mention is this idea of relativistic mass, which is not always super well thought of in the physics community. Basically, like your perceived mass, this is your rest mass, this is kind of the M here in these formulas. So your mass, if you're at rest relative to something, if you divide that by 1 minus v squared over c squared, you get kind of like what's called the relativistic mass, which is basically a measure of its total energy. Your kinetic energy goes insane as you approach the speed of light, which results in all kinds of stuff, because the difference between energy and matter is not they're super tightly related. So you're increasing the relativistic mass by adding more energy, all that kinetic energy. And if you're wondering how much energy gets added as you approach, it basically goes to an asymptote like this sucker. So it approaches, your kinetic energy approaches infinity as your velocity approaches the speed of light. And unless you got infinite energy, you're probably not making a object with mass. You're not going to get it to go to the speed of light. Interestingly enough, if you get into Higgs field stuff, you can't get an object that has no mass to travel at anything but the speed of light through a vacuum. All right, so I want to go over a couple questions just to help you out. This stuff is amazing. Think about it and be amazed. The world is amazing. Incredible energy in everything, difficult to harness, momentum in light and neutrinos and all these massless particles. So here we've got, we're wondering what the rest mass of an object that has a relativistic mass of 7.2 times 10 to the minus 20, if it's going at this speed. Basically, we're just rearranging this guy to solve for m naught, which is really easy. We just multiply this denominator by both sides, and we end up with this sucker. And just plug in your numbers, you got the answer, no big deal. You found the rest mass, which is arguably the more useful thing. All right, as with all the other previous ones, sometimes you want to know the speed if you happen to know the rest mass and the relativistic mass. So if you go and do a bunch of algebra, so again, I started from this point right here, where I multiplied the denominator by both sides to end up with this guy. And then from there, I divided both sides by the relativistic mass and then squared both sides to take rid of this square root, or to get rid of the square root. And then I added this to both sides and subtracted this from both sides, so these guys kind of trade places. End up with that, multiply both sides by c and take the square root of both sides. So if I multiply both sides of the equation by c, it's c squared times 1 minus m naught squared over m squared. And then if I square root both sides, it becomes this. And if you want to know the answer, just plug in the numbers you're given, and you're done. That's pretty much that guy. This one I thought might throw you, so I figured I'd go over it. So you want to know the relativistic speed of an electron that has a relativistic mass 3 times the rest mass. So we start with the same formula we figured out right here. And the relativistic mass is just the rest mass times 3. All of those get squared. All your m naught squareds cancel out, and you got 1 minus 1 over 9, because 3 squared is 9. So whatever the square root of 8/9 is times c. So that's fast, by the way. Yeah, very close to the speed of light if you've got 3 times the rest mass. By the way, there's this awesome Vsauce video. What would happen if Superman punched you in the face? That goes over a lot of this whole energy mass equivalence and just the insane kinetic energies and momentums that happen as you approach the speed of light. That is worth checking out. And I think that is enough. A lot of the rest of this is just use E equals mc squared with the rest mass and all that. So you shouldn't have too much trouble with that. Anyway, hopefully I've given you stuff to think about. Have a great rest of your day.